Okay, let's continue. Sorry for interrupting your break, but I have to teach. So, in principle, what one could do now that one has discussed the signal dynamics of this net magnetization, in principle, one could now go into the imaging bit of magnetic resonance imaging. So basically discuss how these Bloch equations, if they are detected in the transverse plane, or if this net magnetization vector from the Bloch equations is detected in the transverse plane, how this then results in the possibility to do imaging, and then come up with the notion of a K-space and how different gradients, for example a Z-gradient allows for excitation in the Z-plane, so give some localization there, and then how additional gradients turned on for a certain time allow localization of signals in the XY plane. However, as I said, we are postponing these things and don't talk about them right now because they don't work without the really quantitative framework and a good understanding, or at least some understanding, of how the differential equations work that govern this. So we're not talking about K-space and stuff right now, but to at least give you a little bit of an idea how these signal dynamics and the possibility to excite such a system can be used for imaging. I'm talking about these static contrasts right now, which refer to the idea that you do T1 or T2 weighted imaging. Yeah, so that's the thing that we talk about now, because we can, based on what we've just seen in the earlier hour. Also note that things like K-space are not explained yet. So, this is kind of a repeat of what we've seen previously, and also a kind of a first approach to understand how this can be used for imaging. So let's go over it step by step. So what this first equation here says, or what it describes, is the decay from the equilibrium magnetization M0, which is tipped into the transverse plane. And this is described by this exponential function where the t goes in and this time constant is t2. Yeah. So what this shows, or what this equation describes, is just this plot. Yeah, so you should think when you see this equation, okay, there is something M0 here. M0 is actually chosen so that it's 1. So if you put in 0 here, you get exponential of 0. We discussed the exponential function, right? So you get 1 times 1, and then you are here. And then depending on how much you multiply or divide this t by, this decay is faster or slower. So this is the first thing. Yeah, so this is what this describes as a solution to a differential equation, but that's it's not really that important. Now, what you then, what one can add to this is what I also briefly mentioned in the last hour. If you now, after, or basically you do this, and then you don't allow for full recovery in the longitudinal direction. Yeah, so you send a new excitation pulse while the longitudinal recovery has not fully happened. So going back again to this graph. So here, if you would wait until 2 seconds and then send an excitation pulse again, if you then look into the transverse plane, you would still start from 1. If you only wait maybe 1 second, or maybe even, I mean, this is already happening quite a lot. If you only wait for half a second, let's say, and then tip the net magnetization into the transverse plane again, then you would not start out here at 1, but you would start out at, where are we, 0.65. So you would start out somewhere around here. So this means if you, again, look at what's happening, if you do this, if not allowing for full recovery, and you send this pulse at the time that is called TR, so the time between excitation pulses is called TR. So that's a basic sequence parameter. It's time to repetition, and repetition referring to the excitation pulses. If you send this either, I mean, it doesn't really matter whether you wait long enough or you don't wait long enough. In any case, if you look at the behavior in the transversal plane, accounting for the fact that there's also this T1 recovery, you get to this thing, which means that if you plot this, that depending on the TR value essentially the ratio between the TR value and the T1 value, that you either see the full length of the vector that then decays, or you only see a certain aspect of this M0 that then decays. Yeah. So again, M0, the full length, how it is in the beginning, and then it might not have fully recovered. This is this part of the equation, and then because you're looking at it in the transverse plane, it loses over time. It loses its amplitude. Yeah. So far, so clear. Then the next step to talk about is that when the signal acquisition actually happens, because so far we said, okay, there's this decay, so the signal goes down, and then of course the question is, when do you now measure the signal? So do you measure the signal here? Do you measure the signal, I don't know, 10 seconds later or so, when everything has decayed? So of course, what you actually measure at a given time point, or what you measure, depends on the time that you measure it. And the principal acquisition time for the signal in MR is at a time that is called echo time, so TE. Why it's called echo time, this again, one needs to talk about how spin echoes work, which we're not doing, but you can also just view echo time as a time point after excitation. So for example, excitation happens at time 0, and then echo time is stop, echo time at, I don't know, 30 milliseconds or something. Sorry. That's when echo time is. And that means that the signal at echo time is, so this was the signal in the transverse plane at time t, and the signal at echo time, so here you have the t, the signal at echo time then is at what is called TE. So this describes all time points after excitation. This is a single time point after excitation, namely echo time. So this essentially is now the signal that you measure, which depends, as you can see here, on the M0, so the magnetization without any interference by excitation or anything. Then on when the excitation pulse happens with respect to the excitation pulse before, so the repetition time, the time of when the signal acquisition happens, and importantly, the TR and the TE you can choose as an experimenter, right? So you can say, okay, I want to send excitation pulses every 3 seconds or every 1 second, and you can also choose actually when you induce this echo and when your corresponding echo time is. So you also see this in these papers. Usually it says something like echo time 80 milliseconds or something. This refers then to these 80 milliseconds here. So these you can influence as an experimenter, TR and TE. The T1 and the T2 time constant that govern this, and the M0 actually, so the M0, the T1 and the T2, they are given by nature. So the M0, how much net magnetization you have without any, which you have just in the presence of the static magnetic field, that depends on the characteristics of the tissue, and I think I'm missing this second one here, or you can also view this as just this one being relative to 1. If you now imagine that you have 2 tissue types, then one tissue type might have M0, so net magnetization at equilibrium of M0A, and the other one, which is missing here, of M0B. Again, you can also see this is then 1, and this is the difference with respect to the other one, just getting me out of admitting that this is missing. You have for these 2 tissue types also specific time constants of the T1 and the T2. Yeah? Now the game or the task again is to in some way set the TR and the TE, which you can set. So you can decide to do the excitation fairly quickly after another excitation and do the signal acquisition fairly shortly after TE or fairly late after, fairly early after excitation or fairly late after excitation. You can choose that. So to choose this, to choose the TR value and the TE value such as to either emphasize differences in M0 between tissue types, between T1 or between T2. Yeah? And how that works, this is what we want to look now from a kind of visual, intuitive perspective in a little bit detail. Questions about this slide at this point? So what happens is, starting with signal decay in the transverse plane, adding to it the idea that what you have initially in the transverse plane is also rebuilding / decaying if you go in with excitation too early, and then ignoring that you have this whole thing and focusing on the specific time points, and then saying, okay, what can I change as an experimenter, TR and TE, and what does nature give me, M0, T1, and T2? And this is what nature gives us, for example. So the T1 value for gray matter in the brain, what is gray matter? What part? Exactly. And white matter? Yeah, good. The gray matter, so where the neurons of the bodies are, so something like cortex or ganglia, have at 3T, if one measures this, a difference in T1 of, let's say, 300 milliseconds. Of course, this is not varies here and there and so on, but you see that there's a difference between gray and white matter in terms of T1. There's also a difference in gray and white matter in terms of T2. So essentially, whether you do T1 or T2 weighted imaging, you might always be able to see a little bit the difference between gray and white matter. So now we're looking at 3 contrasts. And the first contrast that we are looking at is what's called proton density contrast, which refers to the difference in proton density. And proton density, you should think about essentially just the net magnetization M0A and M0B, which was missing from this other slide. So what is this? So what this means is we talked about that there is this net magnetization at equilibrium, which we then tipped and so on. But this net magnetization at equilibrium is depends on the constituent things of the sample at a specific location. Yeah. So as I said in the beginning of the last hour, we're talking about a single voxel, if you want, or a homogeneous sample. And here we now have 2 voxels, or digenous sample. So in one part of the sample, the net magnetization is M0A, and in the other, the net magnetization is M0B. So in one of them, the net magnetization is larger than in the other one. And this you can imagine if in one of them there are more protons, so if the ratio of protons to area is larger, has a higher proton density, so the net magnetization that is created by these protons on these nuclear magnets is larger than if you are in an area or in a voxel where the density of protons is lower. Yeah, so it just makes a stronger net magnetization in one area and lower net magnetization in the other area. So if this is the case, and you want to be able to detect this, then you are definitely not interested in to look at differences that are on top of that induced by differences in these time constants. Yeah? So the idea is you want to focus on proton density. So in terms of choosing your sequence parameters, so your TR and your TE, you want to not set them in a way that you also get contributions or differences between A and B that are due to difference in T1 and T2. So to avoid anything that might have to do with differences in T1 contrast, what you essentially want to do is take a long TR so that for both tissues the signal has fully recovered to as what it can recover to, right? So one of them, as we will see in the next slide with the picture, can recover to a higher value than the other because at equilibrium they have the same. They don't have the same. That's where the emphasis is. They don't have the same signal at equilibrium, and this is what you want to see. So you allow a long TR to allow for full recovery, and you also don't want to. You are not interested in differences in the decay of the transverse magnetization. So you are just interested in the M0 magnetization of each tissue or of each voxel really briefly after it's tipped into the transverse plane. So you simply measure your signal after really briefly after it is tipped, which means that you set a really low echo time. And then if you see differences, so then you get a signal from voxel A and voxel B, and difference in this signal then should be just due to the net magnetization at time point 0. So here's the picture. So we have now, oops, there's things missing. Sorry, new. That's not what I want. So you see my little things that I do to make things maybe look nicer. Sometimes they interfere. So here we have now a blue curve, tissue A, and a smaller red curve, tissue B. And this shows the T1 recovery for tissue A and tissue B. The crucial point is not so much the T1 recovery, but that at equilibrium, so when the whole thing has recovered, that tissue A has a higher longitudinal magnetization, so M0A, as M0B. Yeah? So there are more protons in tissue A as there are protons in tissue B. Now, if you don't allow for a long TR, and this is why it's interesting to look at the recovery, if you, for example, would tip things already where my cursor is right now, already in the into the transverse plane, then the difference between blue and red is of course smaller, and what you can detect with your sequence is smaller. Here it's the maximum that you can get at, and this is what you want to measure. Means you wait, if you send an excitation pulse here, you wait a long time and then you measure that. Or you have another option, you just send one excitation pulse ever. And then you measure the signal with your echo time immediately or as soon as they are tipped into the transverse plane, yeah? Because you are interested in this difference here. And like I said, two options. You just let the thing to equilibrium, send one excitation pulse and measure it, and then you stop and get the participant out of the scanner. Or if you want to, and this is of course what you want to do, to have kind of not only a single readout of this difference, you repeat this, but so that you can average some data points. But of course, you need to be careful to repeat that not at a too high frequency, but allow for full T1 recovery. Yeah. So this is why then proton density. The idea is for proton density contrasts, one uses a long TR and a short TE. The other things here in this graph, how the different gradients are turned on, this will only become clear once we talk about the Fourier imaging aspects of things. So ignore this. The only thing that you want to focus on here is that radio frequency pulse and the next radio frequency pulse for proton density contrast after a long time, and TE after a short time. So in terms of values, maybe 20 milliseconds TE and I don't know, 3 seconds TR.
I don't know if there's some other mechanical limitations to this, but couldn't it also be possible to just always change the TE and TR and then get like an average for the model, like to one short one and then another one, so because in the end I would have a lot of equations.
Yeah, I mean I mean, now in a way, I mean, if you do it too short, I mean, it's just inefficient, right? If you have it too short, so so think about that, you have these differences, so, and then you tip them, and then you try with a very short TR to tip again. There is nothing to tip. So the difference also that you then can discover is really not there, because not even the signal is there. And if you just look from the difference between these graphs, if you assume that these are valid representations of the functions I showed you before, I mean, just visually you see that the maximum difference is kind of, I mean, definitely here it's smaller. Then whether you do it here or in the very end, okay. But it definitely shouldn't be too small. And the same for the T2. I mean, if you only measure the signal that you tipped after it's fully decayed, then it's definitely too late. And so I would think it's, in terms of the efficiency of the thing, why not do it when you kind of show that you get a good signal? Maybe there is, so in a certain range, you might actually want to do that, and maybe there are also sequences, I don't know where you get this idea from, but maybe there are some sequences that do that. So
it's just an idea, because maybe then you would in the mean have less TR, but I don't
yeah. Potentially, but there will, even if you do that, there will be certain boundaries that you don't want the TE to be too long and the TR to be too small. Yeah? For the simple story, short TE and long TR, especially if you only measure once. Yeah. This is then how the pictures look that look at proton density contrast. So you also see that so gray matter has more protons than white matter, and then ventricles, how are they? They are separated white, and there's a lot of water in them. Yeah, it's just kind of the image that you get from doing something like this. So that was proton density contrast. Is actually also when we then talk about the Fourier aspects of imaging. I should get rid of this here. This is the most basic and easiest to understand, because this really images the net magnetization at time point 0, and you essentially can you try to ignore the decay effects, right? So you ignore that there is the decay and rebuild effects. So you try to ignore the T2 decay, because you measure right after this is tipped, and you also try to ignore the rebuild of the longitudinal magnetization, because you do it after some long time. So you can ignore the relaxation processes if you want this, or you do ignore them. So what you come around more often is that you want to look at T1 contrast, and that means that you are now interested in tissues that have a difference in their T1 time constant. Yeah, so you are interested in detecting T1 time constant differences, and in this thing, you now need to somehow think about, okay, if you want to look at the differences in the tissues that relate to T1 time constants, you have to think not in terms of the endpoints of this process, but when this process happens. So again, this is T1 recovery. And now the idea is that the T1 recovery happens faster for tissue A. So the time constant with which the recovery happens for tissue A is faster. So you're quicker to be at the original level. Now assuming that, not necessarily assuming, but that they have equal net magnetization, you're not actually interested in the value that happens in the very end. You're primarily, or you're only interested in the difference that happens here. Here, if you make the additional assumption that they both actually come to the same end in the end, then which you can of course also normalize if you measure the proton density contrast, then the maximum difference is happening at a time that is not that long after your excitation pulse. So again, here at 0, the excitation pulse, then longitudinal stuff is rebuilding. If you wait too long, their assumption here is that they, as I said 1 minute ago, they come up to the same thing. Here, this is where the difference is that you're interested in. So what you need to do if you're interested in this difference is, again, you cannot measure this longitudinal magnetization, but what you can do is to tip the net magnetization from the longitudinal orientation again in the transverse where you transverse plane where you can measure it. This is what you want to do. So you take a TR that is not that long because you're interested in this time constant. And then with the TE, you again are interested in what happens or the signal that you measure at the time that you tip it, right? So you take an intermediate TR, but you minimize the dependence of the signal on TE by having the TE happen, having the signal acquisition right after the tip. So this is a little bit unfortunate here, this visualization, because if you excite again here, then of course it doesn't have the same value here, but you actually see this difference. Yeah? And this is why the T1 contrast then in the beginning of the next signal acquisition is maximal if you choose a short T2. Sorry, no, you never choose a T2. You choose a short TE. T2 is given by nature. TE is what you choose. So this then shows how T1 weighted images look. So these are the typical anatomical images that you see. So you use an intermediate TR to be sensitive to differences in the time constants, and you choose a very short TE to measure these differences immediately when you can measure them, so after the tip. And yeah, this is then, if you visualize the T1 time constants, how things look. So you have a fairly, so the short ones are with bright gray level values here, and the long ones with long, Jesus, it's the 4th hour. Ja, es ist auch 6. Stunde jetzt für mich. Ne? The short ones are bright gray values, and the long T1 time constants are dark gray level values, so that you have your ventricles being black. Just looks like that if you visualize that. And then finally, if you are not interested in measuring the longitudinal magnetization, so proton density, not interested in T1 differences, but in measuring T2 differences, how should you set your TR and TE? Let's see whether this caught on. Does anyone think they can explain it from these graphs and explain the logic?
I would say you want to choose your TE so you could catch like the most difference, like the highest difference between the two graphs, between the two tissues, and that would be an kind of intermediate point. Yeah, because they're decaying at different velocities, and in the end, everything will decay, so they get closer to each other. So you can choose an intermediate, and the TR you would choose it kind of long, because you need full T1 recovery, and
yeah, and you want very good, yeah.
You want to start the graph on the right from the very beginning, like from the highest level.
Yeah, exactly. So you want to minimize the effect of T1 contrast. In a way, you could argue that okay, you also have minimum T1 contrast here in the very beginning. But then, as you also said, is that of course you don't want to deal with basically no signal. So then it makes sense to wait until the signal that you can get is maximum. So go here until the end. So use a long TR, and then, as you rightly said, use an intermediate TE to be most sensitive to T2 differences. Very good. Yeah, so if you, this is just how to argue this. So if you have a very short or very long TE, there's no effect of T2, because in the beginning it doesn't happen, in the end they are 0, and you want to minimize the T1 dependence and of course the signal. So long TR, intermediate TE, and this is how these T2 images look. If in addition, and this is then now not the way I have it here really clear, if you make sure that you either allow for both effects of spin-spin and local inhomogeneities in your T2 weighting stuff, then you actually measure T2 star, because this is due to both effects. And this is what you do with for EPI. If you make sure that you dissociate the signals that are due to phase coherence loss by actually by a refocusing pulse, and the things that are due to local inhomogeneities, then you get the pure T2. We will get back to that later on, but this is essentially what you use, what kind of the images in fMRI are, almost, with the T2 star difference and the notion of spin echoes and gradient echoes a little bit on the back burner. Yeah. Good. So this was now without talking about Fourier analysis, because we only got so far with Fourier analysis, to give you a little bit of an idea of how one can do some basic imaging. Of course, the question remains, how can we actually localize from the signal that we get, which is the integrated signal, over the whole sample and over also some time? How can we actually get this XY resolution also? So in terms of the Z resolution, we can imagine that, okay, we have a gradient in the Z direction, and this affects the Lamo frequency, and then we excite at a given Lamo frequency. So Z localization is not that hard, but XY localization, this really is where the Fourier stuff is required. And this is what we do in January actually I will briefly have one question once we are done with today about this. So let's look at the summary. So we are now actually finishing the physics imaging part of the introduction to fMRI. So in summary, whole thing starts with hydrogen nuclei that have some spin and can somehow align with external magnetic fields. So this is why we need the external field. Then there is a little bit more nuclei in the parallel state. So we have this net magnetization, and then we get to this idea of describing the net magnetization dynamics with the Bloch equations. With the resonant frequency pulse, which is an oscillating magnetic field, we can tip the net magnetization to the transverse plane, as we mentioned many times today. It's of course magic how this really happens at this point. And then crucially, and this is where we spend most of the time today on, is that after the frequency pulse, there is the relaxation processes happening to the net magnetization vector, one of them being the recovery of longitudinal magnetization, or T1 relaxation, which takes longer. So yeah, in a way it would make sense to call this T2 and not, but I don't want to confuse you, which I have already done, but it's because it takes longer. Why is this T1? It's the second thing that happens in time. Anyway, the decay of the transverse magnetization, which is fast and is called T2, and which one can actually measure, because the MR signal is the net magnetization in the transverse plane. And then in the last bit, we discussed how by choosing certain parameters of a sequence, so when you send excitation pulses and when you measure the signal in interaction with the tissue properties, can at least give you some basic idea of how you can be sensitive to different tissue properties. Yeah? So this is kind of now the end of this first MR imaging discussion. And as I told you before, going into it, I don't think any one of you will now go and say, okay, now I know how to program the Siemens scanner to get this and this out of the brain, this and this signal. It's a first exposure, so that you have heard the terms longitudinal and transverse relaxation, T1, T2, time constants, and a rough idea of what's going on. And yeah, one can, and if one wants, essentially deepen that a lot. We, however, because we are cognitive neuroscientists, have at one point to move on, and this then will be the topic for the next sessions, because we are not only interested in how the physics and the imaging processes work, but also what we actually measure with this and where it's coming from and how it's related to what we're actually interested in, namely neural activity. So this will then be the next big topic, so kind of the biology of the whole thing. Other question right now about the physics imaging aspects of things. I mean, there should be many in a way. And I'm saying, I will tell you how this works in January. So maybe we don't discuss questions about this right now, but get back to it. And there's one thing actually I want to discuss on that, so I stop this here.